All right. So, let's see. How is homework 4 going? It's going
Well, yeah.
reasonably well? Not going yet. If the answer is not going yet, that is fine. Doesn't need to go yet. You still got lots of time. If you,
I did just the first two sessions, so
you did what? I'm sorry?
just the first two sections.
The first 2 sections?
Yeah.
Oh, that's good.
Yeah, that's cool, yeah.
Yeah, that's progress, right?
Yeah, exactly.
The hardest part sometimes is just getting started. It's like if you can make yourself get started and answer one question, then you get a little momentum going and you can scroll through. It's going. That's good. Thank you, Zoomers. If anyone gets stuck, please let me know. I'm happy to help. In particular, I've answered several questions about the idea of saturating the model to test whether or not the piecewise slopes are adequate. The trick to that is making sure that you spread out your dummy codes into the slope sections that have room for them. So you can't load up like all of slope 1 with dummy codes because you've already spent 2 parameters to test change during the first section. Likewise, sessions 7 to 8 is perfectly captured by the line between it, so you can't put any dummy codes there. The rest of them go towards the end. So what I had done in my version of it is just like I started from the top and put in as many as I needed into the first section, and then I started from the bottom and put the rest in section 3. So that should hopefully work for folks. If you run into problems, please let me know, and I'm happy to help troubleshoot. I'm not having office hours next week, but I will be on email. So I will get back to you as needed. Otherwise, I will let you know when your last homework is ready. It will probably go up, hopefully over break. It's going to be overtime invariant predictors. So just another standard homework. There's no final exam, nothing like out of the ordinary. You can get it done as quickly or as slowly as you need to, given the rest of your responsibilities right now. I will be having office hours during finals week. So as is my custom, I'll have my regular office hours on Monday and Wednesday afternoon at 3:30. I'm also going to have office hours that Tuesday and Thursday during all of the time I would have been teaching. So 12:30 to 3:30, give or take, on those days. That way, if you need to get some extra help at the end, you can ask. No problems. All right, I think that's all the schedule stuff I wanted to remind folks of. Anything else I might be forgetting or that you want to ask about? No? Should we talk about time invariant predictors again? Why not, right? We're here. We all made the effort to come in and to sit here or stand here, as it were. No one makes me stand up, but I just I feel better doing it. You know, I feel like if I were sitting down, I'd just start, like this over time, and then you wouldn't be able to hear me. So I'm up, I'm enunciating. This is my aerobic workout for the day. So we were talking about notation and the idea of multiple different sources of explained variance via the predictors. So maybe backing up a little bit might not be a bad idea. I can assume imperfect recall, right? That's a fair assumption? Yes, fair enough. All right, so let's do this one, slide 17. So this is an example of what it would look like for a random quadratic model for time to have a single time invariant predictor added to it. Where time invariant, give me some synonyms again for those. What other words also mean time invariant predictor? Can I share my screen? Wouldn't that be lovely? Yes, I can, and I will. Thank you for the prompt. There, I'm on slide 17 of lecture 7B. What other synonyms for time invariant predictor?
Between person.
Between person, yes. What level? 2, yes. So that means that time invariant predictors contain only one source of variation. They differ between people, and that's it. Person characteristics might be another one. Mm-hmm. So you can mix and match. You can describe these in whatever language you feel is going to be understandable to your readers. Another one might be macro level, although that tends to not be used in longitudinal data as much. But person constant or time invariant, anything like that would work. So this example has education as a quantitative level 2 predictor. Could I have a grouping variable here instead? Sure. Could I have a semi-continuous predictor where it's like if and how much? Sure. So I can put in any kind of predictor I want, and these models do not change their names as a function of what type of predictor it is. It's just time invariant. As with time as a quantitative predictor, when we initially put in a slope for something like education as another type of quantitative predictor, the slope is linear. Like that's typically what the default is when you enter these things. But just to remind you that all of the options for modeling nonlinear slopes, piecewise, quadratic, logging it and fitting something that looks exponential, all of those choices are still available to you for these types of predictors as well. So in this example, people differ from each other in 3 different ways: intercept, linear slope, quadratic slope. That means that my time invariant predictor has 3 potential things to do. And when you have sort of an even model like this, meaning that each beta has a fixed part and a random part, the assignment of variance explained to each of these fixed slopes is pretty straightforward. As a general rule, the new slope for your time invariant predictor explains the U variance that's in its equation. So we have the main effect of education, predicting intercept variance. This right here is actually an interaction, and it has a special name because it's an interaction of variables at different levels. Do you remember the name for that? Starts with a C. CR. Cross level. Cross level, yeah. This is a cross level interaction because time is level 1 and education is level 2. So if we show it this way, this is slide 18, you can see the fact that it's an interaction more readily. So gamma 1, right here ends up being filtered to beta 1, which ends up being multiplied by time. So the interaction of ed by time is what we're actually asking. Likewise, gamma 2, is the interaction of ed by time squared as a 3-way interaction. And in this case, the interpretation of these fixed effects is going to be pretty straightforward because time in this setup is purely a level 1 variable. So it only varies within persons. People do not differ in their time occasions. They don't differ in how long they've been in the study or things like that when they get there. And education, as this example of a level 2 predictor, is purely between persons. So we know that its effect is going to describe how people differ from each other, and it's either differing from each other in the intercept, differing from each other in the linear slope, or differing from each other in the quadratic slope. The rest of the world of time varying predictors gets a lot more tricky, a lot trickier, because most time varying predictors are not level specific. They're not just at level 1, they actually have variance at both levels. So we have to do extra work to try and disentangle their between person effects from their within person effects. So that's why time varying predictors is an advanced topic that could take a month at least, probably 2, to do everything that you could do with time varying predictors. So time is a special case that makes it relatively simple. Okay, how are we doing so far? Sounding familiar? Relatively so? Familiar is good. So we looked briefly at other ways of estimating the same model. So this is what it would look like in single-level SEM terms using wide data instead. Slide 22 has a picture of what it would look like in multi-level SEM. And by the way, multi-level SEM is just multiple multi-level models at the same time. People use the phrase SEM even though there's no measurement model that's operating here. So you would not usually bother to estimate this type of model using multi-level SEM. The reason to do it would be to either include latent variables and actually have a measurement model, or to have models for multiple outcomes at the same time. Multivariate analysis where like one might predict the other, that kind of thing. Where we left off with, I believe, was the idea of systematically varying effects as a new vocabulary word. So slide 25 to start with here. So the question then is, are we allowed to estimate and interpret cross-level interactions if the level 1 variable that is part of the interaction does not have a corresponding random slope? So in this type of example, if beta 1 were a linear slope, say, and beta 2 were a quadratic slope, the absence of the u's here implies what? What does the lack of u's here mean that we're saying about the fixed, the linear slope and the quadratic slope? Yep.
That those linear effects do not vary between people.
Yeah, they don't vary between people. They're fixed. There's no random effects. So each person would have the same linear slope and same quadratic slope. So then this addition of education by time and education by time squared would be allowing people to have different slopes, but not different randomly from each other, different systematically as a function of education. So in this case, like everybody who has the same level of education would have the same linear slope assigned to them. Everybody who has the same level of education would have the same quadratic slope. So varying systematically, not randomly, is the idea. And there are folks who would say absolutely not. If you don't have random variation to describe how people differ from each other, it doesn't make sense to try to predict that non-variation. Because what you're saying basically without these u's is that these slopes are constants, not variables. If you are fitting cross-level interactions and you don't have the random slopes that go here, and they should be there, you will have increased type 1 error. Like really bad, like 50, 60%, depending on the size of the parameters that you put in. Missing random slopes are going to cause the standard errors for the fixed slopes and their cross-level interactions that go with them to be way too small. So I'm talking about the situation in which you do your due diligence ahead of time. You go for and test the random slopes for the effects of time, and you don't find them. So in that situation, it becomes more ambiguous. And in order to say that this is acceptable, we have to change the vocabulary that we would use to describe the level 1 effects. So this box, I'll go back over this again since we did this kind of in a rush at the end of class. This box describes two different scenarios with respect to a cross-level interaction. So for the sake of generalizability here, I've swapped out education with a variable called group. So let's say that you're running an intervention design, you have people assigned to some kind of control group and people assigned to some kind of treatment group, and you want to know if the treatment group grows differently than the control group. That's usually the test of whether your intervention worked, is different rates of change. So on the left-hand side is the situation where that group by time cross-level interaction would be non-significant in the model, and on the right-hand side would be if it were significant. The rows then dictate what happened with respect to the random time slope before versus after including these cross-level interactions. So if the random time slope were initially not significant, if you fit your growth models, it looked like everybody didn't need their own slope, so you didn't put it in, and the group by time cross-level interaction is non-significant, then the word that I would use to describe the linear slope is fixed. Everybody gets the same. It is an estimated constant that everybody shares. On the other hand, if the group by time cross-level interaction were significant, then the way that I would talk about the time slope is systematically varying. It's not that everybody needs their own time slope. It's that the treatment group needs a different one than the control group. So there's two estimated constants instead of one. So it's a middle ground between something that is truly fixed, the same for everybody, and the other extreme, which is where it varies randomly. To me, this seems like a reasonable thing. It seems like it could be the case that there's not enough of a signal to make it look like everybody needs their own, if really there's only two slopes operating in the population. Okay, with me so far? Maybe? Ish? Zoomers, you with me? Thumbs, thank you. Remember, thumbs down is the poop emoji, so let me know if we need any of those. All right. So the second one then here is probably the most interesting possibility. Let's say that you initially did have a random slope for time. So it looked at first like people needed their own slopes. Okay, why do people need their own slopes? Let's find out. Maybe one of the reasons why people need their own linear time slopes is because of what group they were assigned to. And if you put in group by time and it's significant, then I would still call the time slope systematically varying because the random slope went away after including that. So this box right here is like the best case scenario. It describes the fact that what you thought was random variation in linear time slopes was entirely attributable to what group they're in. In other words, the variance that you thought you had at first was gone after you put in this term, meaning it's been completely explained. So that is like an R square of 100 of 1 for that slope variance. That can happen if the slope variance wasn't very large to begin with. But usually this would be an ideal situation, not likely to happen in practice. This box has a blank set of lines because it can't happen. The only way that the random slope variance would go away is because something had to have explained it. The last row then is the situation in which you initially had individual differences in linear change, and it's still there even after you control for group differences in the linear slope, in which case I'd use the word random. So this bottom row would be like, yes, everybody needs their own slope, but everybody still needs their own slope after controlling for group. So there's something else that's causing slope differences that we don't know about yet. So it's still random. So level 1 predictors can be fixed, meaning truly everybody gets the same. They can be random, meaning everybody still needs their own even after controlling for predictors. Or they can be systematically varying. People need different ones as a function of a known covariate only. Level 2 predictors can either be fixed or systematically varying in their slopes. They can't be random. All right. So at this point, the language changes to use the term effect more often than slope, but they're synonyms. So these are still slopes, but the way that we talk about them is effects. Like this is the effective group, this is the effective time, and so forth. So it's a little bit sloppy notation, but that is much more common. These are all slopes, though. Okay, questions on that, or any of that that you want to hear again or differently? No? I'm double-fisted today, trying to get rid of the drinks that I didn't finish before. I just go upstairs and stick them in my refrigerator. So we're cleaning out the fridge prior to Thanksgiving.
Yes, I have
Sure, talk to me.
In the case where random was initially significant but then not, how can we know, or how can we test that significance using likelihood ratio test, or?
Yep.
Okay.
Yep, take it back out and see if it makes the model worse. Yep. So everything that you added and did a likelihood ratio test to see if it helped, the way to test whether it's enough explained is to take it out and see if it makes the model worse. So anytime you simplify, a likelihood ratio test result is going to mean that you made it worse or not worse. Anytime that you add something, you're making the model better or not better.
Mm-hmm.
In the context of cross-random effects models, since I know you're working on that and since you asked the question, the extent to which different items or stimuli are considered exchangeable can be answered by taking a variance component back out. So like if we wanted to test, for instance, whether or not people still differ from each other, we could take out the random effect of interest and see if the model fit got worse. And if it didn't, we would come to the conclusion that, yeah, we've pretty much explained all the reasons why people differ from each other, or items differed from each other, or groups, or whatever source of sampling you're trying to to get rid of.
Good.
Yeah. All of those conclusions, of course, are subject to concerns of power and effect size and all the usual stuff. But yeah, you can take things back out of the model to try and make a point that they're no longer necessary as one of the ideas that you can test. All right. So here's the compromise that I would recommend, and no, this isn't published yet, but maybe someday it will. I don't know if I put it up as a preprint or not. This is probably Date's preprint server land. Basically, what I would recommend is that if you know that testing cross-level interactions is going to be important, so like in the case of an intervention, group by time is the most important thing that you would test because it answers the question of whether groups change differently, which is how you establish evidence that your treatment or your intervention worked. Rather than just relying on a significance test, particularly if you have a small level 2 sample in which that significance test is going to be underpowered, you can compute reliability for that slope. And based on looking at what happened across a range of values, the cutoff that I had recommended in this paper was a slope reliability coefficient of at least 0.2 if you're using REML estimation, which is what you should be doing in small samples, or a cutoff of 0.15 when using ML, in which those variances are going to be downwardly biased. So using these ranges of sample sizes at level 2 and level 1, these are the cutoffs that made it so that the type 1 error rate stayed at where it should be, even when testing cross-level interactions that were completely zero in the population. So paying attention to both slope effect size in terms of its random variation as well as significance is what I would recommend. Which makes sense, because that's what we do for everything else. All right. So what if I had a second time invariant predictor? Can I do that? Sure I can. You can have as many as you have basically people in terms of degrees of freedom. So in this example, I have education still, and I've added in group as a second predictor. And as we had discussed last time, the pattern of the subscripts then, it's gamma O1 and gamma O2 in this first line here. The O is because we're predicting beta 0. The 1 is because education is the first predictor of beta 0 in the level 2 model. Group is the second predictor of beta 0, and so on. So we'd be up to 1, 1, 1, 2, 2, 1, 2, 2 in this type of combination here. So in terms of variance explained, I wanted to do a little interactive kind of demo thing here so that we can talk about that. So pseudo R-square in terms of what piles of variance get explained by what new terms. Let's say if we start with an empty model. So once upon a time, all of our variability was in one pile. The first thing we do is split it into two, right? So we have an empty means random intercept model where we are dividing up our total outcome variability into two kinds, two piles, two levels, between person random intercept and within person residual. And if I compute an interclass correlation, which of these circles is the numerator? Interclass correlation tells you the proportion due to which one?
Level 2 between.
Yes, level 2 between. So the fact that these circles are relatively the same size implies an interclass correlation of about 0.5, to the best of my PowerPoint drawing ability. So the first thing that we would do then is try to describe average change over time. So for instance, if I wanted to go with polynomial models, I might add in a fixed linear time slope. And because time is a time varying predictor, it should explain level 1 residual variance. And so that's why I put this box here as kind of a Venn diagram kind of thing, like the box is going to eat part of the variance. Because this level 1 variance goes down, what is going to happen to my level 2 random intercept variance?
Will increase.
It goes up. So that's, remember that that is going to happen because of the way the intercept variance is estimated. It doesn't mean you did something wrong. Then we take the model and turn it into a 3-pile model if we wanted to test a random linear time slope. So part of the variability, let me go back here so you can see it change. So part of the variability in level 1 residual, once we add in a random time slope, gets reallocated to level 2. So part of what we thought was individual deviations from the line, one of the reasons they could be there is because people need different slopes. They need different lines. And once you give each person their own line, the E variance around that line should be smaller. So we're reallocating part of what we were considering level 1 residual up to level 2 between person. I wouldn't call it an explanation, though. I would call it a reallocation. Because fundamentally, these 3 circles here are all error terms. We don't know why people change differently. We know that they change differently, and we can quantify by how much they change differently from each other. So I would call this a random linear time model. Now, what if I add quadratic time? Well, because time squared is still a level 1 predictor, it should explain the residual variance that remains after this 3-pile partitioning has happened. So if I wanted to talk about R square, I would have to be clear that it's whatever % of the residual variance that remains after controlling for random intercepts and slopes. Because this isn't the same pile that was originally there when I added linear time. Linear time had a bigger pile to take care of. We then split the piles, and so quadratic time has less work to do based on what's left. Okay, with me so far? Now, what if I wanted to test a random slope for time squared? Could I do that? Random quadratic slopes? Sure I could, as long as I have how many occasions?
4.
4 or more. Where is the variability in the random quadratic time slope going to come from? You got 3 choices here.
The level 1 within person?
Yeah, it's coming out of here. It's coming out of here again. Because part of what we were considering E deviations from the line may be because we need to give each person their own version of a bendy line. That makes the residual deviations fit the line better, makes them smaller. So we're reallocating what we thought was within person information to between person. So at this point, to talk about variance explained, we would have to describe it either as per pile or overall. Overall is still coming. We haven't talked about that one yet. We're focusing on per pile for right now. So people differ from each other in 3 ways at this point. There's still the E variance that's around the lines that could potentially explained by time-varying predictors. Okay, with me so far? Any that you want to hear again? Or differently? Okay, so I'm going to exit out so that I can move some boxes. That's my next task here. So our task then is to figure out which pile of variance does each fixed effect in the red boxes explain. There. So time and time squared I've done for you. They explain level 1 residual. And these have to have been here already in order to have the random slope variance that goes with them. Random slopes are always deviations from their corresponding fixed slope. Fixed slope stays in the model even if it's non-significant for that reason. So these boxes here then, I have education as one level 2 predictor, group as another, and for the first boxes, I have times intercept to make the construction of the names parallel, but what I mean is a main effect. The times intercept is meant to help you remember that the way to think about a main effect of a time invariant predictor is as an interaction with the intercept. That's the way I would think about it, because when you go to the equation, like that's where they go. These are the main effects. They are predicting the intercept. So in the same way we can say that these are the effects of education and group on the slope, the main effects are the slopes for education and group in predicting the intercept. So that's why I have it labeled that way, even though most of the time you wouldn't say it that way. Now, which of my 4 piles here is the main effect of education going to reduce?
The first bubble,
The first one. And why do you say that?
Because it's not, has nothing to do with time.
Yeah, and also this and this, the words
Yeah.
match. See, I knew at this point in the semester that we could take all the hints that you want, right? But yes, you're right, because it has nothing to do with time. So likewise then, my main effective group, where does it go?
Same place.
Yep, same place. We're going to put that over here. So we could put these together and look at their joint effect on the intercept, or we could do them one at a time. It just depends on what your research question is. Now what about this one? Level 2 education by level 1 time. So that would be gamma 1, 1.
Would be the second level,
And why do you say that?
because it's not quadratic.
Because it's not quadratic? Yeah, because it matches. Yeah. So this cross-level interaction involving level 1 time, its job is to explain why the slopes for level 1 time differ across people. Part of the reason why the slopes might differ across people is their education level. So to the extent that education matters in predicting linear change, then this box should account for at least some of this bubble. And just as a tie-in to the SEM version of the same way of talking about these models, it is not a coincidence that these are circles. Random effects are latent variables. So if you fit this model in a structural equation modeling software package, you would get an R-square in the standardized solution for how much of the intercept variance has been explained, how much of the time slope variance has been explained, and how much of the time squared slope variance has been explained. If you're not using SEM and you don't have a standardized solution to refer to, we can compute this ourselves relative to the previous model. That's what you would be stuck with if you had unbalanced time, for instance. There is no standardized solution in that case. All right, how about this one? Group by level 1 time. Zoomers, what do you think? What should I do with this? Hopefully there's no cats watching right now. We got 1 vote for level 2 random linear time. Yes, indeed. For the same reason. How about the last 2? Level 2 education by level 1 time squared. Which one? The third one, yeah, the one we haven't done yet. Why? Because they match. So it's the same idea. The purpose of this cross-level interaction is to explain why the time squared slopes differ across people. Maybe they differ across people because of education. And last but not least, level 2 group by time squared. Still this bubble. So I think that beyond just trying to explain how this works, going through this type of exercise in your head when you're building a model is helpful, because you always want to know, like, what is the point of adding this term? What's it supposed to do? And knowing where the variability would be explained then helps you understand, like, what the role of that fixed effect is in the model. Okay. So it sounds like this is going well so far. You ready for a bigger challenge? Just like this much bigger, just this much. You can handle it. I know you can. How about group by education as a two-way interaction? Could I do that? So let me, I can do that. I can do anything I want, right? The answer to could I do that is always yes, okay? Just like if I say coincidence or consequence, the answer is always consequence, always. So in my equations like this, where would education by group as a two-way interaction go? It's got to be in one of these 3 lines. Yep. Education by group would go here. Let me, I'm just gonna put it in. Why not? What's my subscript gonna be? This is the third one. And let me see here. Typing in front of people never goes well. It's close. There, something like that. But I forgot my subscript. There. So education by group. Now, is this a cross-level interaction or no? It is not. It is, I would call it a level 2 interaction because they're both, it's two different level 2 predictors. Just like time squared, I'd call that a level 1 interaction because time is a level 1 variable multiplied by itself as a level 1 variable. So you can have level 1 interactions, level 2 interactions, or cross-level interactions. So then in my box here, which pile should I put this on? Group by education.
First.
Yep, because that's the U that's in its line, right? What about group by ed by time as a three-way interaction? Is this one cross-level?
Yes.
Yes, it is, because I've got 2 level 2s and 1 level 1. Where does it go?
The second level,
And why?
because you have a linear effective time.
Yep. So this bubble is all the reasons why people need their own linear slope. It could be because of what group they're in. It could be because of their education level. What a two-way interaction between those two things would add is allowing the effect of education to differ based on which group you're in, or the effect of group to differ by education. So the latter would be classified as a moderator of the treatment effect, for instance. You might find that your treatment is more effective for people with less education, something like that. So the effect of group could vary by education, the effect of education could vary by group, but what it is the effect on is the level 1 linear time slope. And the same regular rules of interaction terms would apply. Having this three-way interaction in the model implies that you have all of the corresponding main effects and all of the corresponding two-way interactions. I just didn't borrow the boxes from the other slide because it was going to get too messy. But these would all have to still be here. Maybe I should borrow them. Let's do that. I'm going to borrow these real quick. Merp, merp, merp. Copy. Paste. There. It's a little crowded, but you know, we're going to make it work. Group by time, and did I miss one? Where did they go? Oh yeah, no, I haven't put that one out there. Okay. So yes, main effective education, main effective group, group by time, ed by time, group by time squared, ed by time squared. So then now we got everything we need for that one. Last box, where's this guy go? Group by ed by time squared.
Last one.
Yep, goes over here. It's trying to explain why people differ from each other in their rates of acceleration or deceleration. More specifically, half their rate, because that's what the quadratic slope tells you. Cough, cough, homework question. To talk about how the quadratic slope changes the linear slope, we have to multiply it by 2. What you get is half of what you need. Okay, how are we doing? Now what if this bubble wasn't here? What if random quadratic time was not part of my model? What if it looked like everybody could share a common rate of acceleration and it was fine? So here's the same set of questions. Don't come back here. Here's the same variables where education as a main effect and group as a main effect would go on the intercept. Education by time would go on the time slope here. Group by time would go here. Interactions between group and ed would also go here if you wanted them. Now where do these guys go? Their bubble is gone. Wah, wah.
If it didn't really make a difference, wouldn't it just be still that second bubble? Like, because you're squaring out. Are you asking if, like, were you, that we could, or is it possible to still include those even if it's not significant, or not necessarily?
That's the question. It is a point of disagreement among methodologists. So I'm talking about the situation in which we would have tested the random quadratic time slope first before we did any predictor stuff. Not found it to contribute to the model significantly, so we didn't keep it. So then what these two terms would have to do is my question to you. Whether it's okay to even have them at all is the debate. Some people would say no, because the random slope they were supposed to explain is not here. They have nothing to do under that viewpoint. But if you put them in, they could still be significant as what I would call systematically varying effects, meaning that people with the same education level get the same time squared slope, and they're all the same after that. So there's no random individual differences. There's systematically varying slopes if these two things were significant. But what variance would they account for if their bubble is not here?
Would be level 1.
It has to be. Yep.
It's eaten up again.
Because that's all that's left. And when we initially would have added the quadratic time slope, it would have come out of here in the first place. This is where it came from. So it's still in there. So like if you picture, here, let me take this thing here. And it's kind of like the circle's there. I got to get rid of the words inside of it because that's not going to work. Let me change it to 2-point font. How's that? It's like, nope, you can't do that. Well, here. The little circle is still in there. And so that's like, they're on this little bitty circle. That's what they're doing. They're trying to explain that, but it's still in there. So the one thing that people agree on is that if you have not a little bitty circle, but a giant circle, something that is detectable by a significance test, it stays. And we would have to test for the corresponding random slope variance before trying to explain it with anything. So circle first, then boxes. Where the point of disagreement is if the circle is not detectable, can you still try to explain it? I think you can. But I think that reviewer 2 is going to argue about this with you. And when they do that, you can refer them to the Snyders and Bosker's multi-level analysis book or mine for a discussion of these things. So, summarizing in words rather than moving pictures around, fixed effects, meaning slopes, of level 2 predictors by themselves. So not as part of cross-level interactions, but just as main effects or level 2 interactions, they reduce intercept variance. That's where they would go in a multi-level equation. Fixed effects of cross-level interactions depend on how you have modeled the level 1 part of it. If the level 1 predictor that is inside this cross-level interaction has a random slope to it, then the cross-level interaction explains that random slope variance. So in my pictures here, because this interacts with time, it explains the time circle. Because this interacts with time squared, it explains the time squared circle. In the multi-level equation version, it's whatever u is in its line. So u1 refers to the time circle, u2 refers to the time squared circle. And any terms that are in that line explain that u. If they're not, if this level 1 predictor inside the cross-level interaction is not random, then the cross-level interaction has to explain residual variance instead, because that's all that's left. So that's what would happen in a model that looks like this on page 25, where the u's are gone. This cross-level interaction of education and this one with time squared, they would explain the E variance instead. And that practice is somewhat controversial. Okay. Whose head hurts? You can be honest. A little bit. Mine's starting to hurt. See, this is why this is an aerobic activity for me, is because part of the aerobic capacity is literally saying the words in the right order to get this right. Like, this takes effort for me, and I've been reading about this and teaching about these models for like 15 years. This is effortful. So you can only imagine if you are in a model that's this complex, trying to explain it to a general reader who may not even know multi-level models. Like, you want them to be able to follow what you're saying, but sometimes it becomes overly complex relative to what the benefit would be. So the utility of this type of effect size lies in its specificity. We first get a number that describes how much people differ from each other in change. And then we can talk about how good our model is with respect to building that circle specifically, right? Like, it's a very specific kind of effect size estimate. How much of all the reasons why people differ from each other in change has your time invariant predictors, accounted for? The alternative is to think more generally. Now, do you remember back in linear regression? Remember back like in those classes where there was just one pile of variance, maybe some sums of squares and stuff like that, but it was like simpler? Do you remember how to interpret R square in a single level regression model?
Variance explained.
Variance explained. Or if you wanted to talk about it as the R part, what would you say? If you wanted to talk about R square using the words correlation, could you do that? The answer is always yes. Yeah. What is it the correlation of? Two variables, I'll give you one of them. One of them's Y.
The predictors? Or the,
Close, not the predictors, but they're what they do.
the residual? Or
Other one.
The estimates.
Yeah, so I call it Y hat, but it's basically what is the outcome that is created by the predictors. So in my notation, that's Y hat. What does Ariel call it?
The same Y hat.
Y,
Yeah.
Y hat?
Yes.
Okay, so it's Y hat. So another way to think about an R square in a single level regression model is that it is the square of the correlation between Y and Y hat. If R square is significant, if you have your F test for the joint contribution of all the slopes, then there is a significant correlation between Y and Y hat. And the R tells you how big that correlation is. We can do that here. We can put all the piles back together again and just talk about what is the correlation between what the model says and what the data says. So slide 37 here describes that. So the second piece, total R square. This I originally found in the Singer and Willett growth curve book. I'm not sure if they called it total R-square, but that's what I took to calling it in my book. What we can do in any software package, by the way, this is not a manual process of any kind. Even SPSS will do this for you. You can ask it to save a new column to your data set of predicted values from your model. Now, critically, it's fixed effects predicted values only. Only using the fixed effects for this. You take that predicted column, you correlate it with the real one. So y with y hat, square that sucker, that's R-square. So then you can just say, my model accounted for X% of the total variability across time and people. Boom, one number. Your reader's head will hurt less. So I have done this in models where, let's say it's a 3-level model, for instance, where I have like 9 different variance components being estimated, and I don't want to talk about R-square for 9 different things in every single sentence. Go with this. So I like this because it's intuitive. People who know regular regression can follow this logic because it literally is the same definition of R-square. It can be not a good representation of how good your model is, though, for models in which you're not including predictors for every dimension. So let's say, for instance, that you have a fluctuation model where you're looking at something that doesn't change over time, like mood, right? It just sort of fluctuates. It doesn't necessarily get worse systematically in one direction. And let's say that you found that 60% of the variability in mood was between persons. Some people are just grumpier all the time than other people. Could that happen? Sure, it happens. That's actually pretty common with negative affect. It's a more stable trait than positive affect. Given that your focus, though, is on the within-person fluctuations, you may not have any person-level predictors that you care about. So in terms of total R-square, if you only include level 1 predictors, and you do so correctly to estimate their within-person effects, the best you could do is 40% of the variance, because you're not even touching the half of the model that has the 60% at level 2. So from that perspective, like total R-square is not really fair, because like it's lumping together sections of variance you didn't even try to explain. As an aside, I will tell you that pseudo R-square can be done better than just taking the difference relative to a baseline model. There is a way to compute it that involves a marginal model predicted variance in the denominator rather than a baseline model version. So there are some references on your reading list. Reitz and Sturba have a series of papers about this. And they have R packages, of course, that will do this for you. So it'll spit it out nice and easy. Their version prevents negative pseudo R-squares, which is nice. However, they do not have a particular version of R-square that talks about slope variance accounted for. And that's a boo, as I would say, for me, because that's usually something people want to know. So their framework does not explicitly address that. But otherwise, I would direct you towards these resources for doing pseudo R-square in a way that can be more stable, and also potentially less manual typing of things. So I have a SAS macro that I wrote to do pseudo R-square and total R-square. Otherwise, you can do it by hand for just a few values of that. In terms of your homework, it's going to be my version of pseudo R-square, not theirs. So, but there's only a few calculations where I would ask about that. All right, how are we doing?
Well,
Well?
yeah.
All right, well, that's a good answer. I mean, that's like a positive answer. All right, I think I said everything about that. I hope this is going to be like my screenshot, you know, for the, like on the YouTube, it'll be like this slide. Like, what the? Was she drunk that day? Like, no, I meant to do this, I swear. All right. Model building. Okay. There is not a single right answer for how you would go about this process of adding predictors to your models. There's not a one-size-fits-all approach. What I like to do and recommend in practice is to divide your model sort of into pieces. I like to know for each potential level predictor by itself what its contribution is in predicting the intercept and in any slopes that are either random or that I have interest and belief in testing anyway, even if they're systematically varying. So for instance, if I wanted to look at the effect of age and I wanted to look at the effect of reasoning and predicting rates of improvement in response time, I would do one model that has just age in it, let age predict the intercept and all the slopes, do another model that has just reasoning in it, let it predict intercepts and all the slopes, and then I might put them together into the same model. My rationale for doing it that way is that if a predictor's slope is not significant when they're together, so let's say that after controlling for age, reasoning is no longer significant or vice versa. The only way that I would know that it's after controlling for is to know what the answer would have been without that variable involved. So for a given slope that is non-significant, I want to be able to say, is it non-significant always? Or is it non-significant now after controlling for some other thing? Does that make sense, that distinction? So back in regular linear regression land, right, you would typically report a table of Pearson correlations among your variables, right? So you can say, these things are related just by themselves, bivariately, and then you would talk about how the relationship between a predictor and an outcome changes after you control for other predictors, right? It was significantly positive, now it's non-significant, or something like that. Or it was significantly positive, and now it's significantly negative. Ooh, I have suppression. Ugh. But what is the relationship by itself, and what is its unique relationship after controlling for other stuff? Those are two different questions. And I like to know the answer to both. So I tend to, as an initial step, just run separate models with one predictor each, just to get the lay of the land as to whether that predictor matters by itself. And then I would go about combining them in ways that make sense given the research questions and the processes in the field. At that stage, you can either go by variable or you could go by random variance to be explained in terms of adding things in sequentially. So by variable would be something like adding in the three effects of age at the same time. I'm going to let age predict the intercept, predict the linear slope, predict the quadratic slope, something like that. Or I could do something like I'm going to have age and reasoning predict just the intercept. Then I'm going to have age and reasoning predict just the linear slope. That way tends to be, I think, potentially problematic because if you have these higher order interactions, whatever you said at the earlier step is going to be incorrect. Because if you just have a main effect, the interaction above it is going to change how you would interpret it. So I tend to stick in all of the effects of a predictor at the same time to avoid having to backtrack that way. The sequencing of how you would include predictors is, there's no easy answer to that. Usually people do it in layers. So you might first have a model where you include all of the covariates, right? Covariates are variables that someone else cares about who is not you. Like all the things that you have to just control for in order for your results to be believable. Things that are well known to relate to your outcome that are just like beside the point. That stuff might go in first. Then another layer of the stuff that you uniquely care about, the hole in the literature that you're trying to fix, right? That set of variables might go next. And how many layers of holes in the literature there are is up to you in your paper. But that's usually what you would see in a table of results is like, baseline model with no predictors, covariate model, model of interest 1, model of interest 2, something like that. Yeah, so this can be tricky. I would say that there are programming tricks to make this less painful. So one thing that you can do is hijack the idea of data reshaping to work for your advantage. So I've been in many different data projects where there's like 5 outcomes and there's 10 predictors, and the PI wants to see all combinations of everything. How many different models is that if I tried each predictor and each outcome one at a time? If I had 5 outcomes and 10 predictors? It's an easy math one. I can even do this math in my head. How many combinations are there if I have 10 outcomes and 5 outcomes and 10 predictors? That's what I said. That's 50 models, right? If I did every pair. Do you want to run 50 different models? I don't want to run 50 different models. Here's what you can do, though. Take your data set and stack it 2 more times. So you have 1 row per occasion per person to start with. You would then make a new variable that is like a generic predictor column, and you could stack all 10 predictors into that column. Then you stack it again and take all 5 of your outcomes and put them in a single column. Then you use a by option, which it's literally by in SAS. It's like by sort in Stata. If you want to do something by something in R, what is it? Is it a group equals
Group
or
by.
something like that?
Group underscore by.
Group underscore by?
By.
Okay, is that real R or is that the tidyverse crap?
That's tidy.
Yes.
Okay, so that's the tidyverse version. I'm assuming real R has some analog to it though, but you can tell it to do it by something. And then what you do is say, run my analyses by predictor by outcome. And then you get 1 output for all 50. Bang.
Oh, it's like a for loop, probably.
But it's doing it in the data rather
Oh,
than
okay.
doing it in the model. And you should be able then to output a table of fixed effects that, because you have the by, it will be labeled as to which predictor it was in that run and which outcome it was. And you can filter the table to significant results or to anything that you want to just pay attention to. And then it's 1 analysis, like in terms of the code, not 50. So there are tricks to make this a little more efficient if you know just a little bit of the background programming that you can use for this. In terms of evaluating significance, we can always stare at the p-values that come with our new fixed slopes of level 2 predictors. And if we want to lump them together, then we can do a multivariate wald test. So in SAS, it's contrast, it's Stata, and it's test. You've seen this before. Contest, MD, and R. So this can be useful if you want to get a significance test of the joint combination of a predictor in its multiple roles. So like if you want to talk about like what is the significance of including age, where including age meant age by intercept, age by time squared. Like those 3 slopes answer the question, does age matter? You can lump those 3 slopes together with these techniques and get an F-test or a chi-square for it. It is exactly the same idea and architecture as what the model F-test in linear regression is. The F-test that shows up by default in your linear regression results for the significance of the model R-square, that is nothing more than a lumped together set of the slopes in the model with a joint F for their significance. It's the same exact thing. Same with a hierarchical linear regression. If you do it in steps and you get an F-test for the change in R-square, that's exactly what I'm talking about. So if you wanted to do a total R-square and then talk about whether the change in total R-square is significant after adding in, say, 3 slopes for the effect of age and maybe 3 more slopes for the effect of reasoning, you can do that this way. Keep in mind in REML, you can't do anything involving -2 log likelihood if you're adding predictors, because the models have to stay the same with their fixed effects. Denominator degrees of freedom is a thing. I have mentioned this very briefly. There are a few different options that people tend to recommend for multi-level modeling in general, longitudinal data analysis being one special case of that. I will tell you that this stops mattering once you get enough of a sample size. What enough is depends on how complicated your model is. But in general, if you ignore denominator degrees of freedom, then you get a z or a chi-square. So for instance, that's what you get out of M+, whether you like it or not. That's what you get out of most structural equation programs, whether you like it or not. It's also what you get out of Stata mixed by default. You can use estimated denominator degrees of freedom instead, in which you get T's and F's. And it's available in all of the packages. Which particular ones are available varies by package. Kenward Roger is the one that is most recommended if you have tiny samples. It is also the least frequently available. It is inside the Elmer test function in R, though. I have found it's there. Satterthwaite is the one that I used in the book because it's the most general across packages. So it's the only choice that you have in SPSS. You can have it in SAS, you can have it in Stata, and you can have it in R. Briefly, the differences between these have to do with how they reallocate degrees of freedom across levels or given fixed versus random effects. So between within is one option that you can use. This is like your classical repeated measures ANOVA version, where level 2 degrees of freedom would be level 2 sample size minus the number of fixed effects spent. Level 1 is the number of level 2 that you already spent minus the number of level 1 fixed effects. In Satterthwaite, the level 2 predictors will look more like level 2 degrees of freedom, and level 1 will look more like level 1 if it's fixed, but if the effect is random, it moves to level 2. And there's a whole bunch of older research on these suggesting that this does matter if you have, say, like, 5 people in 3 occasions, like that level of small, then you got to worry about this. Kenward Roger takes Satterthwaite and also adjusts the variance components for any small sample bias. So it does result in different standard errors if you use Kenward Roger, not just different degrees of freedom. I would say that, like I said, I'll just say it again. This stops mattering real quick in terms of sample size. So for instance, if I'm using denominator degrees of freedom 20 to reference my T critical value, then T has to be 2.086 to be significant. And infinite denominator degrees of freedom, meaning screw it, I don't even care, I'm just going to call it a Z, is 1.96. So the difference between 20 and infinity, like very few times you would come to a different conclusion. So this stops mattering relatively soon. But if you have very, very little, small data sets, then I would matter that. All right, 140, hitting the wrap-up slide just in time. So take-home messages. This is not going to do well for missing predictors. The cases are getting deleted whether you like it or not. And the purpose of time invariant predictors is to modify the growth curve. So it tells you why interslopes and slopes differ across people. If your effects are random that they're trying to moderate, it explains that random pile. If they're not random, it explains residual instead. Ta-da! There, we made it. That means after break, we get to go through an example with actual numbers and actual code. Woohoo! Questions? Yeah, woohoo. Woohoo said no one ever but me. Can I get a woohoo for it's 1:40 and we're almost done with class? Woohoo for that! Yeah. Except for those of you who have to stay the rest of the afternoon with me. We'll woohoo later. I'm going to woohoo at 3:15 instead. Any questions before we call it a week? Yes.
This one, yeah. Next semester, will we cover the addition of more level 1 and level 2 predictors, right?
Yeah, first thing we're doing is time varying predictors, because you can do it within this type of framework of univariate multi-level models, but only for predictors that themselves don't change over time. If a predictor has individually varying time slopes, then it's not a predictor anymore. You have to carve up its variance into piles in the same way that you would an outcome. And that makes you move from this type of software to truly multivariate, multi-level software, which is done as an SEM or a multi-level SEM in most cases. Yep, that's the first thing we're doing. After we review for like a week or so, though, I think. So maybe the second day. Other questions? Okay.
Yeah, but at this point, are we assuming balanced data, or we are working with the block diagonal estimation?
Depends on your software. If you're going to do any of this in Levon, you got to assume balanced data. If you're going to learn M+ with me, you don't.
Great.
Yeah. How's that? And yes, by the way, we are going to be using M+ next semester for, I think, the majority of it. But it will be on the virtual desktop, and you don't have to buy it. So you will have free access to it, as we currently do in the SEM class. Yeah, because Levon, to do longitudinal analyses in Levon, it's only for balanced time in the standard single-level framework, but their multi-level SEM doesn't have random slopes of any kind. So, like, for longitudinal data, you can't do anything with that. In theory, you could use STAN or, you know, what is the other ones? Any of the Bayesian sort of write-it-yourself stuff. We're not doing that. The models are hard enough without adding that layer of complication, but once you know the models, if you've had training in that software, then you should be able to put it together at some point. So, all right. Thanks for being here, everybody. I will see you after break. I hope everybody gets a chance to step back and recharge, visit family and friends, or do your laundry, or whatever you need to do, right? All right. See you on the other side. Bye, Zoomers.